Hello, I'm Keisuke Harigaya from the University of Chicago. Today I would like to talk about parity, leptogenesis, and SO unification. I first explain how the parity symmetry can solve the strong CP problem, and then discuss the implication of the parity to leptogenesis, ground unification, and the precise measurements of the standard model parameters. Let's first start from the strong CP problem. Strong CP problem is a problem about the nature of the strong interaction. We know that a neutron is made from positively charged particles and negatively charged particles. We may naively expect that the neutron should have a non-zero electric dipole moment, namely the interaction between the electric field and the spin neutron, whose size is as large as the length of the nucleon, namely femtometer. However, experiments say that the neutron EDM should be much smaller than this naive expectation. This suggests that the strong interaction obeys symmetry that forbids a neutron electric dipole moment. The candidate within a standard model is a CP symmetry. In fact, under a CP symmetry, neutron EDM operator is odd. So with CP symmetry, we may forbid the neutron EDM. However, this doesn't quite work because the weak interaction violates the CP symmetry explicitly. Then the question is, why the strong interaction obeys the CP symmetry with good accuracy, while the weak interaction violated a lot? This discrepancy is called the strong CP problem. This strong CP problem can be solved by the parity symmetry. To see that, let's put the neutron in an electric field. Under the parity transformation, electric field changes direction, while a neutron spin does not. You can see that left configuration and the right-hand configuration would have different energy if this neutron EDM is non-zero. So this means that if the parity symmetry is preserved, we can forbid the neutron EDM and solve the strong CP problem. At the microscopic level, parity symmetry is exchange symmetry between left-handed particles and right-handed particles. This parity symmetry cannot be the exact symmetry of the standard model because of weak interaction. In fact, only left-hand particles couple to the weak gauge bosons, while right-hand particles do not. So weak interaction explicitly violates the parity symmetry. So to implement the parity symmetry, we must consider a spontaneously broken parity symmetry. For this, we introduce a new gauge boson that couples to the right-handed fermions and realize parity symmetry as an exchange symmetry between the weak gauge boson and these new gauge bosons. We then give a large mass to this new gauge boson by breaking this new SU2 symmetry, SU2R, which is a parity partner with a weak gauge symmetry, SU2 left, at the high energy scale. In this way, we can ensure that weak interaction violates parity symmetry, while the strong interaction preserves the parity symmetry, approximately. So this is the easiest implementation of the spontaneously broken parity symmetry. We have the standard model Higgs, HL, whose vacuum exclusion value spontaneously breaks electric weak gauge symmetry. Then we can just introduce a parity pattern of the standard model, HL, and spontaneously break the new gauge interaction by a large wave of this new Higgs bosons. Now let's discuss the implication of parity symmetry to leptogenesis. In the Standard Model, we have a neutrino that only has left-handed particles. Then with parity symmetry, we need to introduce a new fermion that is a parity partner of the Standard neutrino, which is called the right-handed neutrino. It is known that this right-hand neutrino can explain the observed baryon symmetry of the universe via so-called leptogenesis, which is the following. These right-hand neutrinos can decay into lepton and Higgs. It can also decay into anti-lepton and anti-Higgs. If those two decay rates are not equal to each other, the decay of the right-hand neutrinos in the R universe can create non-zero lepton asymmetry. This lepton asymmetry can be converted into baryon symmetry via a non-particle process called the Weeks-Farrion process. This is called the leptogenesis. In leptogenesis, the mass of right-hand neutrino is constrained for the following reason. The asymmetry in those two decay modes is given by the quantum correction. At the tree level, the decay rate of the right-hand neutron is proportional to its Yukawa coupling Y, while its quantum correction is proportional to the cubic of the Yukawa interaction. The asymmetry and decay rate is given by the interference between a tree-level interaction and the loop interaction. As a result, lepton asymmetry is proportional to the square of the Yukawa interaction. However, this square Yukawa interaction cannot be arbitrarily large. This is because right-hand neutrino, via its Yukawa interaction with the lepton and Higgs, creates a non-zero neutrino mass via so-called seesaw mechanism. Then after requiring that the Standard neutrino mass created by the seesaw mechanism does not exceed the observed neutrino mass, Yukawa coupling square and hence lepton symmetry is bounded from above as a function of the right-hand neutrino mass. Then after requiring that the observed baryon symmetry can be produced by leptogenesis, we obtain a lower bound of the right-hand neutrino mass. This bound of the right-hand neutrino mass also gives bound on the parity breaking scale. The right-hand neutrino mass is given by this dimension 5 operator involving two right-hand neutrino and two parity partner of the Standard Higgs. And because of parity partner, because of parity symmetry, if we have the second term, we also have this first term. Then after the parity symmetry breaking scale, parity breaking, second term gives right-hand neutrino mass, and the first term gives the Standard neutrino mass. So then the Standard neutrino mass is given by right-hand neutrino mass VL square divided by VR square and other possible contributions, assuming that the Standard neutrino mass is not given by fine-tuning between those contributions. And after requiring the lower bound of right-hand neutrino mass from the successful leptogenesis, we obtain lower bound on the parity breaking scale to be 5 times 10 to 12 GeV. So we need relatively large parity breaking scale. As we will see, this has a great implication to the proton decay rate in the S-on-T unification. Now let's move on to the discussion on the implication of parity symmetry to ground unification. It turns out that the gauge symmetry structure required by the parity symmetry is a subgroup of the SO10 gauge group. So we start from the SO10 gauge symmetry and spontaneously breaks it into the parity symmetry gauge group at the high energy scale. Then we break this parity symmetry gauge group down to the standard gauge group by the vacuum exclusion value of HR. So this is a structure. As in the standard SO10, all of the standard fermions plus a right-hand neutrino can be embedded into a single representation of SO10, namely 16 representation. This is SO10 unification. In this SO10 unification with parity, there are 4 UV-free parameters. 1, unified gauge coupling. 2, mass of the gauge boson that mediates proton decay, which is called XY gauge boson. And the mass of another gauge boson that does not mediate proton decay. Then finally, we are the parity symmetry breaking scale. From those 4 UV parameters, we should explain 3 IR observable, namely 3 gauge coupling constants. Since we have 3 observables and 4 UV parameters, we can obtain one relation among those 4 UV-free parameters, which we choose to be the mass of the XY gauge boson as a function of the parity breaking scale. This is a prediction. X-axis is a parity breaking scale, VR, and Y-axis is the mass of the XY gauge boson that mediates proton decay. And the blue band show our prediction from the unification. So here, non-zero values from the blue band comes from a possibility that there might be some so-called threshold correction, small quantum correction to the gauge coupling constant at the SO10 breaking scale, which we require to be sufficiently small. This red shaded region is already excluded by the proton decay surge at the super K. And red dash line, up to red dash line can be probed by hyper K. Then after putting a lower bound on the parity breaking scale, VR, from leptogenesis, you can see that most of the Weber parameter space can be probed by Hyper-Kamiokande. Okay, let's discuss the implication parities, leptogenesis and grand unification to the measurements of the star model parameters. So we have discussed the parity symmetry breaking by the parity pattern of the star model Higgs. So here I show the possible potential of the star model Higgs HL and its parity partner HR. The first 2 terms, the usual one bottle potential made from quadratic term and quadratic term of the star model Higgs. Second term is the parity partners of those terms. Then the last term is a possible quadratic coupling between HL and HR. But you can see that because of parity symmetry, there are very small number of parameters in the potential of HL and HR. And it turns out that we can obtain strong prediction because of the limited number of parameters. In particular, with a little computation, one can show that the star model Higgs quadratic coupling in the low energy effective field theory after parity symmetry breaking nearly vanishes at the parity symmetry breaking scale. So this is a theoretical prediction on the Higgs quadratic coupling and its energy dependence. So x-axis is the energy and y-axis is the Higgs quadratic coupling, the standard model. Starting from the value 0.1 around electric scale, because of the quantum correction from some interaction, in particular the topical coupling, quadratic coupling gets smaller and smaller and cross zero at the high energy scale. In our theory, this scale is a parity symmetry breaking scale. And this point where the quadratic coupling nearly vanishes is sensitive to the standard parameters, in particular the top quark mass and the strong coupling constant. Now, from the successful leptogenesis and the constraint from the proton decay, the range of the parity symmetry breaking scale is limited. Then we can now, from this constraint and the relation between vanishing quadratic coupling and asymmetry parameters, we can obtain the prediction on the asymmetry parameters, which I show here. Here, x-axis is a strong coupling constant, and y-axis is a top quark mass. Then this blue band shows our prediction. It will be interesting to confirm this prediction by future precise measurements of the asymmetry parameters. Here is a summary of my presentation. Spontaneously broken parity symmetry can explain the CP conservation of the strong interaction. Leptogenesis and gauge coupling unification can be consistently incorporated with parity symmetry. The key experiment to prove the theory is a proton decay search and precise measurement of some standard parameters. That's all. Thank you.